Hi everybody, it's Mrs. Mancuso. I am continuing on with the January 2018 exam, so make sure that you have that ready. We're on part B2, which are the part twos, and I want to make sure that each time we are talking about what makes a good point-worthy answer. You'll see right here, this question is worth 1 point. So the first one is convert the melting point of mercury to degrees Celsius. So I need to go grab my reference table, look up mercury. Mercury is element 80, and I go to table S and I find its melting point. And its melting point is 234. And if I want to have it converted to Celsius, this is in K right now. So on the reference tables, it tells me K is equal to Celsius plus 273. So that means I need to go minus 273. I'm punching it in, 273 minus 234. I get negative 39 degrees Celsius. All right, draw a Lewis electron dot diagram for a molecule of hydrogen fluoride. So hydrogen fluoride is HF. It's covalently bonded. So I'm going to do it right up here while I have a little bit of space. Hydrogen and fluorine are going to share 2 electrons. So there's the dot and the dot from them sharing. Fluorine already had unshared pairs of electrons on the other sides. So I need to make sure that I show the 2 dots above, to the right, and to the bottom, as well as the line connecting HF. Or another way that you could do it is you could actually show the 2 dots, and then here are the 2 dots for those. This shouldn't be a line. Somehow with my finger it just made a line there. All right, next one. Show a numerical setup for calculating the quantity of heat in joules required to completely vaporize 102.3 grams of water at 100 degrees Celsius and 1 atm. So they're asking me to solve for Q. So I go to the back of the reference tables and I go to the Q formulas. And Q is equal to mHV. And I know I want to use that one because I want to vaporize. So now to show my correct numerical setup, I would say Q is equal to, all right, the mass is 102.3 times, now I need HV. So I go to the front of my reference tables. HV for water is 2260. So there is my correct numerical setup. Q is equal to 102.3 times 2260. Next one, state the color of methyl orange indicator that's placed in 0.1 molar NH3. So first of all, NH3 is a base. And so because it is a base, I know the pH is greater than 7. So what I need to do is I need to go to table M and see what color it is in a base. Table L is right above it, reminding me that NH3 is a base. All right, methyl orange, when it is a base, it would be yellow. So yellow would be my answer here. All right, next one. The bright line spectra for 4 elements in a mixture of elements is shown in the diagram below. Write the letter of each element present in the mixture. So here's my mixture. This line right here came from element A, so I know I've got A in my mixture. And then these lines seem to come from A and D. So now I know D is in my mixture, and I can follow this line is here from D, this line's here from A, this line's here from A, this line's here from D. So that's it. I can now go across and say, all right, X. Are any of X's lines, like here's the line from X and it is not in there. So element X is not in my mixture. And Z, here's a line from Z and it's not in there. So Z is not in my mixture either. So the letter of the element present in the mixture would be A and D. All right, explain in terms of electrons and energy states how the light emitted by excited atoms is produced. This, I feel like, is asked very, very frequently. So, as electrons move from high energy excited state, so that's when they're out farther away from the nucleus, to lower energy, ground state, they release energy, as light. So I use light because they use light in theirs, and I made sure that I talked about electrons, and I made sure I talked about energy states. So when the electrons are excited, so let me just draw an atom here. Here's the nucleus, here's an orbital, here's an electron. When it absorbs energy, it can move out here to a high energy state where it's excited, but when it goes back to ground, that's when it releases the energy. So as electrons move from high energy excited to lower energy ground, they release energy, and their light is unique for each different atom. Okay. Rubidium and iodine have different chemical and physical properties. Some of them are shown here. The first one is state the chemical property of iodine. So here's iodine over here. Bluish black, that's a physical property. Forms ionic bonds with active metals. Ooh, I would write that right here. That is a chemical property. Subliming is physical. That's changing from a solid to a gas. A specific heat is, again, a physical property. It's how much heat would it have to absorb to change temperature. So I want the chemical property, so I would write forms ionic bonds with active metals. I would write it exactly as it's written there. Compare the atomic radius of an atom of iodine to the atomic radius of an atom of rubidium when both are in the ground state. So I'm going to go look them up on the periodic table, or I could look them up on the table after the periodic table. But rubidium is in group 1, so it's a left side loser, which means it's very large. And iodine is also in period 5, so they have the same number of rings, but iodine is going to be smaller. So I would write here, iodine has a smaller atomic radius than rubidium. Okay, so I know my writing is too large with this font. Let me make it a little smaller. Okay, next one. Compare the electrical conductivity of these two elements at standard temperature and pressure. So rubidium is a metal, so the metal is going to be able to conduct electricity, and the non-metal is not. So I want to write that. So rubidium can conduct electricity. Iodine cannot. Again, I'm going to make it a little smaller so it fits in here. There we go. I have compared the electrical conductivity. Base your answers to this. Given an unbalanced equation, first of all, I got to balance it. So, to balance this reaction, 4 P's, so I would right away put a 4 there in front of PCl3, and then 4 times 3 is 12 Cl's, so I would need 6 Cl2s. So there's my balanced reaction. State why this is a synthesis reaction. This is synthesis because it is forming one product. When you do synthesis, you combine things to form one, so I have formed one product. All right, show a numerical setup. Sorry, got off my page here, gotta find it. Okay. Show a numerical setup for calculating the percent composition by mass of chlorine. So I want to figure out how much chlorine is in PCl3. Oh, and they even told me the gram formula mass of PCl3. So I have 3 chlorines. So I want to have Cl3 on the top. I want to have PCl3 on the bottom. And I want to go times 100. So first thing I'm doing is looking up chlorine. And chlorine is 35.5. So 35.5 times 3. I've got 106.5. The bottom they told me is 137 and then times 100. That is my correct numerical setup. All right, the decay mode for the first and third step is shown above the arrows. So this is an alpha and this is a beta. And the decay mode is not shown in the diagram for the second step. And then it tells me the half-life. So explain in terms of neutrons and protons. So we're going to have to write this out. Why uranium-238 and uranium-234 are isotopes? So they are isotopes because they have the same number of protons, but different number of neutrons. That's the definition of an isotope, to have the same number of protons. They're both uranium, so they both have 92 protons, but uranium-238 has 4 more neutrons than uranium-234. All right, identify the decay mode particle emitted from TH234. So I go up here, and what I want to do is I want to say, okay, for this arrow, 234 to 234. So the substance I release has a mass of 0. And then 90 here, 91 minus 1 would give me a 90, and I have to make sure these are balanced. So that is also a beta. So my answer here would be beta. That would be the decay mode. All right, and then determine the total time that must elapse until only 1/16th of a sample remains unchanged. First of all, I got to figure out how many half-lives is 1/16th. So 2 half-lives would be a quarter. 3 half-lives, 2 times 2 is 4, times 2 is 8. 4 half-lives would be 1/16th. So I want 4 half-lives. And it says determine the total time. Well, up here, it told me that TH234 has a half-life of 24.1 days. So 4 times 24.1 days would give me 48.4 days. That's the total time that it would take for 4 half-lives to occur. Okay, I'm going to stop right there, and we will do part C in the next video.